Hello everyone, my name is Lorenzo Colantonio. I am a FAIR PhD student working on spoke number 5, and today I would like to show you my work on transformer equivariant graph neural network. We studied the community detection. Community detection is a widely studied problem in network science, where the structure of the task is inherently invariant to permutation of both node indices and community labels. For this reason, we introduce a graph neural network that combines message passing and transformer module designed to be equivariant not only to graph isomorphism, but also to permutation of community assignments. Our approach enhances the ability to learn multi-scale patterns and non-local dependencies. Moreover, the results obtained highlights the potential of integrating equivariant transformer with message passing to address symmetry-rich problems in network analysis. As I said, we studied the community detection problem. We are interested in identifying groups of nodes in a graph that are more densely connected to each other than to the rest of the network. We can measure this property using the modularity shown in the pictures. Communities provides insights into the underlying modular structure of complex systems with application in social networks, biology, information system, and physics. The model was trained using the following loss function composed by the weighted sum of two terms. So we have a cross-entropy term and an unsupervised term, namely the modularity. As you can see, this term is a proxy of the modularity shown before. After the training, we would like to use the model in an iterative fashion, where at each step it receives the noisy output of the preceding iteration as an input. In our work, we build a message passing transformed that takes in account the permutation invariance of the task. The MPT is a feature-wise permutation equivariant k-layer graph neural network. As you can see, at each layer, the node representation are updated through a message passing algorithm implemented using two transformer modules. So we start with node features for each node. We stack them in order to obtain an edge features. We use those edge features and we pass them to a phi transformer in order to obtain the messages ij. We can aggregate all the messages and stack them to the original node feature of the node, pass them to a second transformer gamma t, and updating the nodes. In the final step, all node embeddings are aggregated and fed into a final transformer module, after which a softmax function is applied to produce the community assignment, yi. Now we present the preliminary results obtained. The model was evaluated on two different datasets. The first one is the LFR benchmark, an artificial dataset widely used because it reproduces typical properties of real-world social graph. In particular, both the community size and the node degrees follows power law distribution. As shown, MPT clearly outperforms the Leiden algorithm, one of the current state-of-the-art methods, across all the three evaluation metrics: variation of information, normalized mutual information, and F1 score. We also tested the model on the planted graph coloring problem, which can be interpreted as a special case of non-assortative community detection, where the nodes belonging to the same community have a lower probability of being connected to each other. We choose the case with the size of the network being equals to 1000 nodes and the number of colors Q equals to 5. At the moment, we are running the model on additional datasets, and we would like to study the explainability aspect of our model. Finally, our goal is to release a preprint with all the results as soon as possible. Thank you all for your attention and goodbye.